Hi everyone, my name is Francisca and I'm in group 13 and I'm explaining the question. So the question says that the characteristic equation of a stable system is given by A0S4 plus A1S3 plus A2S2 plus A3S1 plus A4S0 is equal to 0. Determine the conditions which must be satisfied by the coefficient of the characteristic equation for the system to be stable. So this is the characteristic equation, and the S4, S3, S2, S1, and S0 are the poles, and the A0, A1, A2, A3, and A4 are the coefficients of the characteristic equation. So the question is saying that what condition of the coefficients will make this characteristic equation stable? So we use the RH method to solve this question, and my colleague will solve the question further. Thank you.
To fill the RH table, you follow a specific pattern of alternating coefficients and cross multiplication. The step 1 is filling the first two seed rows. The first two rows are populated directly from the coefficient of the characteristic equation. Row S4 takes every other coefficient starting with the first one, that is A0, A2, and A4. Row S3 takes the remaining coefficients, that is A1 and A3, and fills the rest with zeros. For step 2, that is calculation of row S2. To find the values for the next row, you use a determinant-like calculation. You look at the two rows immediately above it, that is S4 and S3. The first element, S2 column 1, you multiply the first element of the S3 row by the second element of the S4 row. Subtract the opposite diagonal and divide by the pivot, that is the first element of the S3 row. The second element, S2 column 2, you use the same pivot A1, but look at the next column above, that is A4 and 0. Now for step 3, which is calculation of S1. This follows the same logic, but now you use the rows for S3 and S2 as your base. The pivot becomes the value we just calculated for S2. The formula shown on the slide is the result of cross multiplying the S3 coefficient and the S2 result. So the final step, which is S0. By the time you reach the bottom, the calculation has simplified significantly. The last non-zero coefficient A4 essentially drops down to the S0 position.
First, we take the given equation and remove the denominator to form the characteristic equation. When we expand and group like terms, we get a standard cubic polynomial given here. Next, we build the root table using the coefficients of this polynomial. The first two rows come directly from the coefficients, and the third row is calculated using the root formula. What we are really interested in is the first column of the table. For the system to be stable, every value in the first column must be positive. So from this table, we get conditions like a greater than 0 and k plus 1 greater than 0, and another expression involving k and a. Solving these gives us the ranges of k that keeps the system stable. That's the whole idea from the polynomial. Build the root table, and we use the first column to determine stability. Thank you.
So I'll continue from this slide. In this slide, we are looking at the conditions under which a system exhibits sustained oscillations. Sustained oscillations occur when a system continues to oscillate with constant amplitude over time, meaning there is no damping of growth. The system is perfectly balanced. Now, let's break down the conditions here. We start with the equation k plus 2 minus k plus 1 over 1 is equal to 0. This equation represents the balance point in the system, where oscillations neither decay nor grow. To simplify it, we rearrange the terms. A multiplying k plus 2 minus k plus 1 is equal to 0. This step eliminates the denominator and makes the relationship clearer. From here, we solve A, which gives us A is equal to k plus 1 as numerator and then k plus 2 as the denominator.
So, in continuation from where my colleague left off, when the row in the rotary table is 0, we use the row directly above the s squared row to form an auxiliary equation. This equation describes the roots that are causing the oscillation. So from the table, we realize that the s squared row coefficients are a and k plus 1. So in a stable oscillating system, the roots lie exactly on the imaginary axis of the s-plane. Therefore, we will substitute s equal to j omega into the equation. Therefore, we will have j omega squared equals minus k plus 1 all over a. The auxiliary equation acts as a bridge, and also it takes the boundary condition from the root table and links it to the physical frequency omega of the system's movement. Thank you.
Okay, so this is the final step of the problem. We are given that the frequency of sustained oscillation is omega, which is equal to 2 rad per second. And from root Ari's auxiliary equation, we have j omega all squared to be equal to minus k plus 1 all over a. So plugging in omega, which is equal to 2, j times 2 all squared will be equal to minus 4, which will be equal to minus k plus 1 all over a. That means k plus 1 all over a is equal to 4. Therefore, a will be equal to k plus 1 all over 4. And that's exactly what we see here on the slide. A is equal to k plus 1 all over 4. So at this point, we've used the given frequency to express A in terms of k. So the next step usually is to combine this with the earlier condition from the marginal instability to solve for both k and A. So this is the final step shown here. Thank you.
Okay, so we can see over here from the previous expression that A is equal to k plus 1 over 4. Now, we've also established that A is equal to k plus 1 over k plus 1. Since A is equal to k plus 1 over 4 and also equal to k plus 1 over k plus 2, we can equate these two conditions, which will give us this expression here. Yeah. But then when we solve for k, we get our k value to be equal to 2. We then input the k value into the previous condition over here, that's k plus 1 over 4. And we get our final answer to be 3 over 4, which is equal to 0.75. Therefore, giving us the value of A. Thank you very much.